Hello and welcome. Today we are going to explain a real mind-bending technology topic in a simple way, but without dumbing it down. If you have ever heard phrases like quantum computers, qubits, and this could break encryption, this is for you.
And we will do it as a friendly, educational conversation. We will use everyday examples, a few tiny thought experiments, and we will end with a clear summary you can repeat to someone else.
Quick reminder before we start. If you are enjoying these deep tech explainers, subscribe to Randomer's GUI and turn on notifications so you do not miss the next one.
Also, if you are watching this as a live stream, top like. It helps a lot. All right, let us jump in.
Big question first. What is a quantum computer, really? Is it just a faster computer?
Not exactly. A classical computer is built on bits. Each bit is either 0 or 1. A quantum computer uses qubits, and qubits can behave differently. The key is that qubits can represent information in a way that uses quantum physics, especially superposition and entanglement.
Let us start with superposition. People often say a qubit is 0 and 1 at the same time. That sounds like magic.
It sounds like magic because it's a shortcut sentence. A better way, a qubit has a state that can be a combination of 0 and 1, described by two numbers called amplitudes. When you measure it, you get a normal 0 or 1, but before measurement, you can treat it like a blend that can interfere with itself.
Interfere, like waves?
Exactly. Think of water waves. Two waves can add up to make a bigger wave or cancel each other out to make the surface flat. Quantum states behave similarly. The power comes from designing computations where wrong answers cancel and right answers reinforce.
So it's not infinite parallel universes doing all answers. It's wave-like math that can amplify the right answer.
Perfect. That is the practical intuition.
Now, entanglement. This is the spooky one.
Entanglement is a relationship between qubits where they share a combined state. It means you can't fully describe one qubit without describing the other, even if they're far apart. In computing terms, entanglement lets you create correlations that are stronger than classical correlations, and those correlations can be used for certain algorithms and error correction.
So, entanglement is not instant messaging faster than light, but it is linked outcomes when measured.
Yes, measurement outcomes can be correlated in a way that classical systems cannot mimic, but you can't use it to send a normal message faster than light.
Okay, next confusion. If a qubit can be in a blend of 0 and 1, why can we not just read all the answers at once?
Because measurement collapses the state. When you measure, you get one outcome. You don't get a full printout of the blend. So quantum computing is about arranging operations, so the probability of measuring the correct result becomes very high.
So, the computation is like carefully choreographed interference.
Exactly. Choreography is a great word here.
Let us anchor this with a tiny example. Suppose we want to find a special item in a huge list, like searching for the one correct password in a sea of wrong ones.
In a classical computer, if you have no structure, you might have to check many items. Quantum computers have an algorithm called Grover's algorithm that can speed up unstructured search. It doesn't give an exponential speedup, but it can reduce the number of checks from roughly n to roughly square root of n.
That's still huge. If n is a billion, square root is about 31,000. That's a big drop.
Right, it's a quadratic speedup. Not magic, but impressive.
And the famous encryption breaking story comes from a different algorithm.
Yes, Shor's algorithm. It can factor large numbers and compute discrete logarithms efficiently on a large enough fault-tolerant quantum computer. Those are the hard problems behind many common public key systems, historically including RSA and some elliptical curve schemes.
So, does that mean quantum computers will break the internet tomorrow?
No. Two reasons. First, the quantum computers we have today are noisy. They're not large enough and not stable enough to run Shor's algorithm at the scale needed to break real-world keys. Second, the world is actively transitioning to post-quantum cryptography, which uses different math problems believed to be safe against quantum attacks.
That transition is already happening in standards and products.
Yes, it's one of those rare cases where a future technology is pushing the present to upgrade security early.
Randomers GUI viewers, if you want a video specifically about post-quantum cryptography and what changes for normal users, write PQC in the comments and subscribe so you catch it.
Now, let us address the elephant in the room. If quantum computers are so powerful, why are they so hard to build?
I've heard the phrase, quantum states are fragile.
That's the heart of it. Qubits need to maintain coherence, meaning the delicate quantum state must persist long enough to compute. The environment is like a noisy room that constantly bumps into the qubit. Heat, electromagnetic fields, tiny material defects, even cosmic rays can introduce errors.
So, we cool systems down, isolate them, and still errors happen.
Exactly. Many leading approaches use extremely low temperatures, sometimes near absolute zero, because thermal motion causes noise.
What are the main ways to build a qubit?
There are several. Superconducting qubits use tiny circuits at cryogenic temperatures. Trapped ion qubits use individual ions suspended by electromagnetic fields and manipulated with lasers. There are also photonic approaches using light, neutral atoms, spins in silicon or diamond, and more.
So, multiple hardware stacks, like early computers had vacuum tubes, transistors, different architectures.
Great analogy. We're in a period where the best long-term path isn't fully settled. Different platforms have different strengths. Superconducting systems often have fast gate operations and strong industry momentum. Trapped ion qubits often have high-fidelity operations but can be slower. Photonics has a potential scaling story. Each has challenges.
You use the word gate, so quantum computers still use logic gates?
Yes, instead of classical gates like and or, quantum computers use quantum gates that rotate and entangle qubits. Under the hood, these are matrix operations on state vectors. You build circuits from gates, then measure at the end.
That sounds like linear algebra heaven.
It is. If you like vectors and matrices, quantum computing feels like physics and math holding hands.
But you mentioned errors. In classical computing, we can correct errors easily with redundancy, like parity bits.
In quantum computing, error correction is possible but expensive. The tricky part is you can't copy an unknown quantum state, so simple duplication doesn't work. Quantum error correction encodes one logical qubit into many physical qubits so that errors can be detected and corrected without directly measuring and destroying the information.
So, when people say we have 1,000 qubits, it may not mean 1,000 useful qubits.
Right. Many of those may be physical qubits. A fault-tolerant system might need thousands or even millions of physical qubits to produce a smaller number of logical qubits with low error rates, depending on the target workload and the error correction code.
That's a sobering reality check.
It is, but it's also why the field is exciting. Progress in hardware fidelity, connectivity, and error correction stocks can shift the curve.
Let us talk about what quantum computers are good at today, not in a sci-fi future.
Today, we have what many call NISQ-era quantum, noisy intermediate scale. They can run small circuits, demonstrate research experiments, explore chemistry simulations on toy problems, and test algorithmic ideas. Some quantum computers are also used as research platforms for hybrid algorithms that combine classical optimization with quantum subroutines.
Hybrid, like the classical computer does the heavy lifting and the quantum computer is a specialized coprocessor.
Exactly. Think of it like a GPU. A GPU isn't universally better at everything, but it can accelerate certain workloads. Quantum accelerators may eventually play the same role for certain classes of problems.
What kinds of problems feel quantum native?
Physics and chemistry are natural because molecules are quantum systems. Simulating molecules accurately can be hard classically, and quantum computers represent quantum states more directly. That could help in materials science, catalysts, battery chemistry, and drug discovery.
And beyond chemistry?
Optimization, certain machine learning primitives, and cryptography-related tasks can be relevant, but we should be careful. Not every optimization problem becomes easy. Quantum speedups often depend on specific structure.
That's an important realism point. People hear quantum and imagine instant solutions.
Right, quantum computing is not a cheat code for all computational difficulty. It gives new tools, and for some problems, those tools are game-changing.
Let's do a mini quiz for the audience. I'll ask, you answer, then we reveal. Ready?
Let's do it.
Question 1. Does a quantum computer try all answers at once and then read them all?
Answer: no. It uses superposition and interference to increase the chance of measuring the correct answer. Measurement gives one outcome.
Question 2. Can entanglement be used to send faster than light messages?
No. Entanglement creates correlations, but it doesn't transmit controllable information faster than light.
Question 3. Are today's quantum computers powerful enough to break standard internet encryption right now?
No, not at real-world key sizes with fault tolerance, but the future risk is real enough that the world is moving to post-quantum cryptography.
If you got all three, you're already ahead of most comment sections.
And if you didn't, that's why we're here. Also, remember to subscribe to Randomer's GUI if you want more topics like this explained without confusion.
Now let us talk about the how in slightly more detail, but still friendly. What does it mean to apply a gate to a qubit?
Imagine a qubit as an arrow on a sphere called the Bloch sphere. The arrow direction represents the qubit state. A gate is like
Now, let us talk about the how in slightly more detail but still friendly. What does it mean to apply a gate to a qubit?
Great question, because this is where quantum computing stops being a mysterious buzzword and starts feeling like an actual machine you can reason about. A gate is basically an operation that changes the qubit state in a precise, controlled way.
Like a classical NOT gate flips 0 to 1 and 1 to 0.
Exactly, but with a twist. In a quantum computer, gates can do flips, but they can also rotate the state and change its phase. That is why people say quantum computing is linear algebra in hardware. The state is like a vector, and the gate is like a matrix that rotates or transforms that vector.
That sounds intimidating.
It can, but we do not need heavy math to get the intuition. Here is a friendly mental picture. Imagine a globe with the North Pole labeled 0 and the South Pole labeled 1. A qubit state can be pictured as an arrow pointing somewhere on or inside that sphere.
I've heard of this. The Bloch sphere?
Yes, the Bloch sphere is a visualization tool. The idea is pure qubit states can be mapped to points on the surface. Classical states, 0 and 1, are just the poles. Superpositions are points in between.
So, where does a gate fit in this picture?
A single qubit gate is like grabbing that arrow and rotating it by some angle around some axis. That's it. A gate is a rotation. Some gates are 90-degree rotations, some are 180, some are more subtle.
That already makes it feel less mystical. It's geometry.
Exactly. Now, the second key idea is phase. Phase is like the timing of a wave. Two states can have the same measurement probabilities but different phase relationships, and phase is what makes interference possible later.
So, a gate can change phase without changing the chance of 0 versus 1 immediately.
Yes, and this is where quantum gets powerful. In classical computing, if nothing changes the probability, we would say nothing changed. In quantum computing, phase can change everything about what happens next, because later gates can convert phase differences into probability differences.
That sounds like the hidden lever.
That is a great way to say it. Phase is the hidden lever.
Can you give a simple gate example that people actually mention?
Sure, the Hadamard gate. It's one of the most common gates in basic explanations. If you start with a qubit in 0 and apply Hadamard, you get an equal superposition of 0 and 1.
So it creates the both possibilities state.
Exactly. In our Bloch sphere picture, it rotates the arrow from the North Pole to the equator. Not exactly the only way to describe it, but conceptually, it moves you from a definite state to a balanced superposition.
And then measurement gives 0 half the time and 1 half the time.
Yes, but here's a cool part. If you apply Hadamard again, you get back to the original state. So Hadamard is like splitting a wave and recombining it. If nothing happens in between, it recombines perfectly.
So two Hadamards cancel.
In a sense, yes.
And if something changes phase in between, the recombination changes.
Exactly. This is the simplest way to feel interference. Think of a two-path experiment. First Hadamard creates two paths. A phase flip is like changing the sign on one path. Second Hadamard recombines. Depending on whether the sign changed, the output becomes 0 or 1 with certainty.
That's incredible. So a tiny hidden phase change can produce a big visible difference at the end?
Yes, that is quantum computation in miniature. Hidden phase, then recombination, then visible probability change.
Okay, that's single qubit gates, but you also said entanglement needs two qubit gates.
Right. Entanglement doesn't happen if every qubit is manipulated independently. To create entanglement, we need gates that link qubits. One famous one is the controlled NOT gate, often called CNOT.
What does C naught do?
It's like this. You have two qubits, one is the control, one is the target. If the control is 1, you flip the target. If the control is 0, you do nothing.
That sounds classical so far.
It sounds classical, but the magic appears when the control is in superposition. If the control is half 0 and half 1, then the CNOT gate creates a state where the two qubits become linked. You can end up with a bell pair, which is a simple entangled state.
Walk us through it slowly.
Start with both qubits in 0. Apply Hadamard to the first qubit. Now the first qubit is an equal superposition of 0 and 1, while the second is still 0. Then apply CNOT with the first as control and second as target.
So if the first is 0, second stays 0. If the first is 1, second flips to 1.
Exactly. But because the first is in superposition, the result becomes a superposition of two joint outcomes, 0, 0 and 1, 1. Then, when you measure, you get either 0, 0 or 1, 1, each about half the time, and the results are perfectly correlated.
So if I measure the first and get 0, the second must be 0. If I get 1, the second must be 1.
Yes, and that correlation is not because the qubits secretly decided ahead of time. It's because the combined state is a single object. That is entanglement.
And this is not faster than light messaging.
Right, you can't choose whether you get 0 or 1. The outcomes are random but correlated.
Now, how do we use these gates to actually compute something?
Quantum algorithms often follow a pattern. Step 1, create superposition so you represent many possibilities. Step 2, apply a problem-dependent operation that changes phases in a way that marks good solutions differently than bad ones. Step 3, apply more gates to turn those phase differences into probability differences. Step 4, measure.
So the whole game is designing the phase marking and the recombination.
Exactly. That's why people call it amplitude amplification, phase kickback, interference patterns, and so on. Different words, same concept.
Let's connect this to Grover since we already mentioned it.
Grover is a beautiful example of this pattern. You start in an equal superposition over all possible items. Then you have an oracle that flips the phase of the correct item. That phase flip is invisible if you measure immediately because it doesn't change probabilities directly.
It's hidden.
Yes. Then you apply a diffusion operation that reflects amplitudes around the average. That reflection transforms the phase-marked difference into a real increase in amplitude for the correct item. Repeat that cycle and the correct item becomes much more likely.
So the gate story is not just abstract, it's literally the engine of Grover.
Exactly.
And Shor?
Shor is more complex, but at a high level, it also uses interference and a structured transformation called the quantum Fourier transform to reveal periodic patterns. Again, phases matter. Interference matters. Measurement extracts the useful pattern.
The quantum Fourier transform? That sounds scary.
The word sounds scary, but the intuition is familiar if you know the idea of decomposing a signal into frequencies. The quantum Fourier transform, in a loose sense, is a way to reorganize phase information so that periodicity becomes visible when you measure.
So it's like turning a hidden rhythm into a visible spike.
Exactly. That's a great way to say it.
Now, let's step back. If gates are the operations, what's the program in quantum?
The program is a circuit. You choose a sequence of gates. The order matters. The circuit depth matters because more gates means more opportunity for error.
So in practice, even if an algorithm is great on paper, the hardware might not run it well if it requires too many gates.
Exactly. That's why people talk about hardware-aware compilation. You take an abstract circuit and map it onto the gates your device can actually perform given its connectivity and noise characteristics.
Connectivity.
Right. In many devices, not every qubit can directly interact with every other qubit. You might have a grid where each qubit can only do 2 qubit gates with its neighbors. If you need to entangle distant qubits, you have to move information around using swap operations.
Which adds more gates, which adds more noise.
Exactly, so architecture shapes what's feasible.
This is starting to sound like real engineering constraints, like networking or chip design.
It is. Quantum computing is physics and engineering and computer science at once.
Now, quick small reminder because some people are listening and enjoying this style. If this is useful, tap like and consider subscribing to Randomer's Guide for more long-form explainers.
Now, let's talk about how noise shows up in gate language, because that's the practical part.
Yes, because noise sounds like one thing, but it's many things.
Exactly. In gate terms, noise means the gate you intended is not exactly the gate you got. Maybe the rotation angle is slightly off, maybe the phase shift is imperfect, maybe some unwanted interaction happened with a neighboring qubit, maybe the qubit lost energy or its phase drifted randomly.
And then measurement error, where you read it wrong.
Yes, measurement is its own step with its own error.
So in practice, quantum computing is not apply perfect gates.
Right. Real devices apply noisy gates, which is why people focus on gate fidelity. Fidelity is like a score for how close the real operation is to the ideal.
And 2-qubit gates are typically harder than 1-qubit gates.
Exactly, because linking two qubits requires stronger interactions and more precise control. Many platforms can do single qubit operations quite well, but 2-qubit operations are the bottleneck.
Which is why creating entanglement at scale is hard.
Yes,
Now, you mentioned error correction earlier. Can we connect it to gates?
we can. Error correction is like running additional circuits that detect errors without measuring the actual data directly. You use extra qubits, sometimes called ancilla qubits, to interact with your data qubits through gates. Then you measure the ancillas.
And the measurement tells you about errors.
It tells you a syndrome, basically a pattern that indicates what type of error likely occurred and where. Then you apply corrective operations, often using a simple lookup or decoding step.
So, error correction is not a single magic button, it is an active process.
Exactly. It is like a constant maintenance routine running in the background. You repeatedly check for errors, collect syndrome information, and make small corrections so the logical information stays